Yes.
Great. Welcome everyone, especially to people who could not join in the morning session. I'm going to talk a little bit about hybrid power plants for future power systems and what is a hybrid power plant and uh, how this is a new research area which has been developing. So especially for the PhD students, it is something to look upon. That's what we believe, at least, that this is a growing research area. So what is a hybrid power plant? If we look at a little bit of from the historical perspective, then what we can see is that in 2016 there was a one power plant. This is by Vattenfall in UK, who hybridized this 3.6 megawatt wind to with 4.95 megawatt PV. Was still a pilot project, but this was one of the first megawatt level hybrid power plants came up in modern times. Well, when I say that this is one of the first, then the question comes how, because we have been seeing many hybrid projects. The previous hybrid projects have generally considered mainly also diesel, so they are not completely renewable hybrid. But at the same time, there have been many microgrid and mini grid or hybrid systems to catering island systems, island networks. But this trend of developing a large scale hybrid power plant, that is kind of new. And this is what we mainly focus on today. Is called utility scale grid connected hybrid power plants, generally 50s to hundreds of megawatts, at least to start with. And then came the Kennedy Energy Park, which really started all these discussions with was Vestas and WindLab in Australia in 2018. And then there are a few more in Kavital in 2018 as well in India. But there are also, I don't know, visions for much more hybrids to come in future. Like there is Whitridge is one of the facilities that has been discussed in Portland in US. But in India, there has already been launched 1.2 gigawatt of auctions for hybrid, but they have vision of 2.5 gigawatt of hybrid. And at the same time, different policies are also coming in. Like in India, this national wind solar hybrid policy came in. The wind industry in Denmark, they have this mega wind policy, and their hybrid solution was one of the major policy drivers that came up a couple of years back. And last year, I think GWEC, the Global Wind Energy Council, they have also recognized hybrid as one of the major uptaker or major instrument for green transition in future. So now with all these trends, so let's try to define it a bit. What is utility scale, co-located, grid connected? So there are quite a few nouns being placed one after another to restrict what we are looking at. So like I said, utility scale is basically means it's 50s or hundreds of megawatts. They are grid connected power plant, so they have to provide all the grid services or at least meet the grid code requirements there. And then they are generally owned by a single owner or or the developer. And then generally they are developed with a vision like any other power plant to maximize the value from the market. So as opposed to a hybrid system, which is more about maximizing the value for the society in terms of security of supply, this is maximizing the value for the power plant owner. Like it shows here, we will have wind power plant, solar power plant, and battery storage. They come with individual controllers, and then we build up a separate hybrid power plant controller, which talks with a hybrid energy management system. And energy management system is the brain which decides on which market, how much service or how much electricity to be sold to based on the forecast and the market predictions or market signals. If we look at around the world, so this is from Wind Europe. They have a database of hybrid power plants around the world. So we also see that many hybrid power plants are coming up around the world everywhere, including Herringvliet, for example, is the one of the recent ones which has come up in Netherlands, in Europe. But there are huge vision, for example, Asian Renewable Hub in Australia, the vision of having 11 gigawatt of hybrid in order to meet the load in the islands here in Indonesia and other places, the Pacific. So we see that all the hybrids are being developed around the world. Why this trend started? This sounds like something which could have been done many years back, but what we see that suddenly that the cost of wind and solar have been coming down, and around 2019 they have become comparable. If you see the cost and the capacity factors, well, the solar still has a capacity factor a bit lower than wind, but then most of the best located wind locations are also being taken over, at least in onshore. Then that also means that the capacity factors of wind are also going down at the same time due to solar technology. They are increasing the capacity factor. So as a result, what happens that we have two comparable resources or comparable technology, and then comes that from the cost benefit analysis, the combination of them leading to the hybrid power plant. From the system operator or societal point of view, why this is an interesting concept is that then land acquisition is one of the major challenge for onshore anywhere in the world, and optimal utilization of land. Instead of building a separate wind and solar power plant, you can optimize the land usage and develop a hybrid power plant. That's one of the basic value for the system operator or the society. Delayed requirement for transmission infrastructure. If you want to look into the visions in terms of carbon decarbonization or CO2 reduction or emission reduction all over the world, they are very ambitious targets anywhere. But at the same time, in order to meet them, there is a transmission or the distribution system infrastructure need to be reinforced extensively, which is a time-taking process. But with the same connection point, if we can connect more renewables, that also allow better utilization of the network resources. So it's a win-win situation in that scenario as well. And that's something we also see in Denmark more and more nowadays. Improve grid stability and security, as like what Damien was showing before, that with increased share of non-synchronous generations, the security and stabilities are getting challenged. But then at the same time, if the availability of any power plant is increasing because you have more complementary resources, then that also increases that the grid support, grid services from those power plants are also going to be more valuable. Like I mentioned, more risk integration from the policy point of view, so that's another bonus point. And more flexibility will, as compared to individual wind or solar, combining them individually or together with storage, also increases the flexibility that would allow for more decommissioning of the fossil fuel generation. And then this is more with storage, that if the network cannot take for any reason renewable energy at certain point, that would mean curtailment, like what Damien was showing before. And in such scenarios, having a storage inside the power plant can be valuable to reduce those curtailment. From owner or developer's point of view, definitely the cost reduction and revenue increase at the angle. But cost reduction, where does that come from? Infrastructure cost, like I mentioned, land cost, or optimal use of the electrical infrastructure, for example, or other development infrastructure like access roads or vehicles for transporting the different components and all those things. Those can reduce the cost. Reduction can be achieved from there. Project development, if you need to do permitting, there is also delay, and that also the delay in project development also incurs cost. So now you are doing the permitting for the lower number of projects with hybrids. So that's also another benefit. Shared resources in reduce internal costs and joint site development like soil investigation or weather measurement or resource assessment, or even analysis or development of models or project analysis. All those tasks reduces as compared to two different individual projects. From park performance point of view, so you have less fluctuating power production. That means that you are increasing the electrical infrastructure, be it cable, be it transformers, at least mainly the grid connection transformer. So you can, it's getting more and more difficult in any place, mainly developed countries like Denmark, to get a grid connection point. So if you get a grid connection point, then you would like to utilize that to the maximum value. And then, like I mentioned, increase in flexibility and able to go into different markets when you have, especially you have storage. So then we identified what are the different research aspects in hybrid power plants. Like what I've been discussing, it sounded like, okay, this looked like a very developed research product or developed product where you just take and combine two generating technologies and you are done. But it's not the case. But when we started the discussion on what should be the focused research in terms of hybrid power plant, at least the utility scale hybrid power plant, and then we had multiple national and international stakeholder meetings through Danish Wind Hybrid Power Plant Forum and IA Wind topical expert meetings. And then we identified, well, these were identified mainly from the Danish forum, but still we identified these are the major topic of research. And they are not prioritized, but I'll go into very briefly individually to all of these, but I will go into details about some of them with more detailed discussions. Energy management system, it's like which market should you go to, how much you should bid based on the forecast, and how to consider those forecast uncertainties. At the same time, how to use your storage, especially if you have battery storage, because whenever you use it, there is also lifetime or degradation cost of the storage. So considering that, and this is also Ruji's PhD is on this, and if you have listened to Ruji's presentation earlier, then you already have some idea what is meant by energy management system for hybrids. Sizing and siting. How do you do resource assessment, because the underlying weather model is the same. So how do you do resource assessment at the same time, because if you do separate resource assessment, then they are then you do not capture the correlations or anti-correlations between wind and solar. Physical design optimization, how do you minimize the land usage? How do you minimize the physical interactions? And I'll come into details. And how do you hybridize those storage technologies, or how do you optimally size the components in wind, solar, and storage? Electrical design and control, how do you make utilization of the different assets there? How do you maximum utilize the network components, be it cables or transformers? How do you control them? Should there be a hierarchical control or distributed control or a mix of them? Which kind of grid services can you provide? How can you provide those grid services? And then another like black start capability is something like what Damien also touched upon on morning session, is that hybrid power plants, due to their increased availability, is a candidate, especially if you have storage as well for black start. But then how can you provide black start from a hybrid power plant? Uncertainties and forecast. Until now, we have been mainly working with the wind forecast, like we as in the generally wind forecast is much more mature than solar forecast, but that doesn't mean that just you can combine in wind and solar forecast, because as a if you are forecast provider per se, or you are a transmission system operator, then how do you combine this wind solar forecast for different purposes? And this purpose can be reduction of penalty due to not meeting the bid in the spot market, or it could be minimization of the variability in your wind and solar power, or whatever. So that means that when you combine wind and solar together with storage, there is a control aspect to it, and then come as a combined for the whole hybrid power plant, you need to have a single forecast output. And how do you do that is an open question. Grid emulation and advanced test, what we discussed from we heard from Paul and also a little bit from Philip earlier, is that they are very much, well, mainly from Paul, the standards are very much for wind, and then most of the requirements are for wind or solar per se. There is not a single requirement for the combined hybrid power plant, and that's a critique we hear from the industry, that some of the requirements should be at the PCC or the point of connection or point of common coupling for the whole hybrid power plant. But then the question comes in that why then that test requirement or test method should be developed for individual assets, especially when you are combining different types of technologies in provision of some of those services. And even for the whole hybrid power plant, what can be the type of test methods, and when we develop those test methods, how to validate those test methods and models and test methods there. And then it is beyond that is to integrate it. So what we have been discussing is mainly for electricity market, but beyond this we can go to the other markets or include to other sector coupling with hydrogen or heat or transport sectors as well. Go into details, a little bit details about the sizing, and we do not go into the details because this is also a very complex topic. But for people who have been working with small scale sizing projects and then using many commercial softwares, for example, Homer or other, so this problem is quite different in that sense, and I'll come to that later. So this is a sizing optimization problem which we are developing, as we say. So there are as opposed to a hybrid system where you have few turbines which are very dispersed over large area generally, or you have small scale wind turbines or small scale smaller solar panels, the major difference is the between the interaction between them, but also the choice of turbines and other things does not play that huge role, because the storage plays a major role there. But not to diverge the discussion into hybrid systems, but rather stick to the hybrid power plants utility scale. So you can see that there are different loop of optimization. So this is the outer loop of optimization, where you take into consideration all the individual components. So for example, this one CodeRes is an internal tool which can look at the weather model and design the resources for any particular location in terms of wind speed, but also it can give other like temperature for the solar panel performance analysis, solar irradiance, but also, for example, rainfall, which can be used for example for wind turbine lifetime analysis, because they can create leading edge erosion in the wind turbines. Then you can in the optimization, you do not know what should be the size of the wind turbine per se in terms of hub height or rated power or the diameter of the wind turbine. So that becomes another variable in this coupled optimization. So you design a wind turbine, so you need to have a generic wind turbine model which take different input of the hub height and rated power and all those parameters, and you use that similarly. And then when you have put multiple wind turbine in your optimization, the next layer is to include the wake losses. Otherwise, your AEP calculations will be very wrong. So that's another angle to it. And this is already done for wind power plant design, for example, today. And then when you have combined them, it get lead to the wind power plant. But then you connect it to the PV power, you bring in the PV power or PV panels into the equation, and then the new layer of interaction comes. For example, when you're trying to mitigate minimize the land usage, so the shadowing or the we call it flow change in flow because of the heating of the solar panels in the wind might happen, especially when you have few kilometers full with solar panels there. So when you bring that in, and then comes the battery degradation model, that how do you use the battery, and more you have to integrate the energy management system with the operational strategy here. And when you use the battery degradation, and then when you use the EMS, that would impact on the battery degradation. And when this EMS is brought into the whole optimization picture, that would again start changing your wind and PV panel calculations as well. Like when you start putting battery, you will probably try to change your type of wind turbine you will put, or even different mix of different types of wind turbines. So you can see that this is a so difficult problem, and here this is assuming everything is deterministic and everything is known. We did not bring in the uncertainties as well in here. Already this has become a so difficult sizing problem, and we also did not bring in the physical optimization in terms of cable physical designing, like how many kilometers of cables you should put, what should be the size of the inverter for the PV, and how should you put the storage inside the wind turbine or separately, or for example for provision of reactive power, should you put an auxiliary device, or you should get it from the wind and the PV and the battery converters. So just to give you a flavor that this is a very difficult problem, but then we will show a case study from a very smaller scale problem, just to appreciate the difficulty of the problem. So there was a tender uh, in India, which was a very interesting tender, and so this is a part of our ongoing project, hybridized Indo-Danish project. So we took this as an example. So the power purchase agreement requirement was that every day there can be 9 peak hours, and that peak hour is defined from 6 to 9 in the morning and 18 to 24 in the afternoon. And HPP should provide peak power for 6 peak hours. Out of these 9, for 6 hours, they should provide peak powers. Otherwise, they will be penalized. But even the difficult challenge is the 6 peak hour will be provided to the hybrid power plant owner one day before the operation. So while designing, you don't know how would you design. So and then there was a winning bid which decided the peak tariff to be 81 euro and the off-peak tariff to be 32 euro. So we thought that let's try this an example and try to design a hybrid power plant for that. But this has become so difficult problem. So the starting problem is that when you are designing, let's start with a deterministic design. So which are the peak hours you should choose? So what we looked into is that these are the wind and solar profile there, and the peak hours are so peak prices, we looked at the price history for last couple of years for this one location in India, and then we tried to correlate this peak with price history. So when the price in the historical price were going up, we say that is the peak hour. So what does that mean? This peak profile is based on the historical prices and assuming that in future that history will remain the same, and then the system operators will keep on asking every day, these are the peak hours and you provide me the peak power. And these are two close by location where we have real data, and then the data showed that the capacity factor for solar was around 24% and wind was around 30% based on real measurements from 2 power plants. When we designed based on this, we found out that for a contract capacity, that means the grid connection capacity was given as 300 megawatt. For a contract capacity, the wind installed capacity should be 171 megawatt, solar should be 378 megawatt, battery 80 megawatt, 3-hour battery. Then when you add them up in terms of power, so that comes out 630, 640. So that's like almost more than 2 times the grid connection capacity. So this is the first takeaway point, is that only the value of hybrid power plant comes in when you start overplanting. So if you have 300 megawatt grid connection, then you will not put 300 megawatt of wind and solar. And this is what we always see in all the projects coming up in all the around the world. So this is the key feature of hybrid power plant. But with overplanting, then comes that there is a natural. It is natural that there will be curtailment because you are overplanting so much if you cannot put it in your storage. So what we did is that we compared if we had only solar or only wind, or wind and solar, and the optimal solution, which is wind solar battery, lithium-ion battery, how do they compare to each other for this case? So what we see, only solar. In India, solar is the cheapest source, and solar has comparable capacity factor with wind, is the cheapest generation. And for 300 megawatt of solar, it costs 29 euro per megawatt hour. Whereas for wind, that is 38. If you put wind and solar, that's 32. And for optimal solution, that's 39. So the optimal solution is the most expensive solution. But in terms of profit generation, the only solar is not generating that much profit for this peak non-peak kind of case. Whereas the optimal solution is almost getting 2.5 times more profit as compared to only solar. Also, wind and solar per se combined is also giving much more profit, double profit as compared to only wind and solar. Next, we saw that during peak hours, our optimal solution is providing more energy as compared to the off-peak hours. That's how it is designed. But still, it is not that it is only generating during the peak hours. It is quite getting flexed, but that means that this is sort of intuitive, but it's good to put out there that this is where the flexing is happening. So the generation during the off-peak hours is getting transferred to the battery for the peak hours. But then we said we did another interesting study that instead of this standard power purchase agreement, in the power purchase agreement you have fixed price, right? For each kilowatt hour you sell during the peak hour or off peak hour, you get certain revenue. But if you just need to go in and bid in the market at the market price, the market clearing price, how does that look like? When we did that, we saw that there is no value of wind, there is no value of battery storage, and this only asks us to put a certain amount of solar. But then the point of that is that you put 377 megawatt of solar, so everybody will keep on putting solar because that's where they will earn the revenue. But then you are not providing the peak services, which is requirement for their meeting their peak load in India, and that's why they are asking for this additional kind of services. And then your traditional conventional solar power plant does not help. Another example we saw that is if we just say that we have evening peaks and we design for that, then with that kind of certainty, there is no value of battery storage. You only put wind and solar there, be designed for that, and then that is performing, but it is a costly affair, but it is not getting as much as revenue as compared to the base case when you also have the flexibility to provide some expensive generation in the morning as well for the peak power, peak price. That shows that why regulation driven market is still important for hybrid power plant in different places, and only market driven prices are not sufficient at this point for hybrid. And at the same time, policies like only evening peak, considering only evening peak, can give a very different solution as compared to the example case what we are having. But if you remember, we had pinned down that we have a very correlated assumption in our price profile, market price profile. So next we tried to take those pin out. So like I said, so this is the blue curve is the load profile or the electricity price profile we had in from there, the system, and then we put highest correlated the orange profile is the price profile based on which we designed. But then what we say that we start bringing in a randomness in those price profile generation. So we generated many random price profiles, but with all those requirements. That's out of those 9 hours, it can be 6 hours peak, and it's between morning 6 6 to 9 and evening 18 to 24. So having done that, so when we look at the correlation with the load, so you can see that the correlation is not varying that much within that range. It is varying between 0.34 to 0.375. So that as opposed to 0.3975 or something like that for maximum correlation, the result based on which our results was previously. So, and then for each of these simulations, each of these seats, we ran the exercise of designing the hybrid power plant again. And then each of those points were giving us very different solutions. So if we look at net present value, so any of those price profile would make your NPV dilute from 100 to 65. So if you are choosing one of the very optimistic price profile, you will get €100 per megawatt hour of NPV, whereas a most pessimistic one will give you 65. So getting financial support for this kind of projects is hugely difficult when you have this kind of uncertainties and you go to the bank to get P5 values. Same goes in terms of wind power installation as well. So you can see that different price profile are letting different wind power installation as well, or solar power installation. Solar is not changing that much, it's changed from 340 to 380, but wind is changing from 0 to 150. So that is the kind of uncertainty we have in the tender, and this is a real case of tender happening today. So that also brings in that we cannot continue with deterministic methods anymore. So we need to move into the stochastic method. And I'm not going to go into details about stochastic methods now, also because we have not solved the problem yet. But what are the uncertainties to look into? So this different price profiles, whether there is also year-to-year variability. If you just take 1 or 2 years of data, it's highly probable that you will end up into one of those corner solutions. Rather, you should include the variability over many years. Cost data, or not only the cost of today, you need to think about the cost in the future as well, and the cost is changing at the time as we speak. Financial parameters, there is also uncertainty in there, how the inflation would move in future. Energy management system should consider the forecast error in their energy management. Right now, we assume deterministic model in the energy management system. So that's a major scope of improvement in there. And then reliability and availability, which I'll touch in the next slide briefly. So reliability. So in the previous model, we started putting in the reliability parameters for each of the components, the wind turbines, PV panels, the transformers, the inverters, and whatnot, based on the historical data. And then we started to see what is the impact. And what we saw there is that the blue one is when you don't consider availability or reliability indices, or you assume 100% availability, and this is done over the sensitivity of the cost for different cost parameters. And what we see that even reliability does not impact on the trends per se here, but it does impact, and we are plotting NPV here, but it does dilute the value quite a lot when we start bringing in the availability. I think I had some other figures, but yeah, that's fine. We do not have time for all of them. But then in terms of sizing, we have many open questions coming up. How to include all those factors like I discussed before in sizing and physical design. in terms of resources, correlations and uncertainties, climate change aspects, because we have been always working with historical data, but with climate change coming in, how to take into account that factor. And this is for also for wind or solar individually, but especially for hybrid, because hybrid is a kind of a technology which is supposed to work solely on market and very less on individual power purchase agreements or contracts. And then different kinds of markets, which market to go in terms of electricity, what kind of uncertainties to be considered there, markets beyond electricity, how to share the infrastructure, and also the taking the cognizance that the first mover into the market will reap some of the benefits, but as more and more people would come into more and more hybrid power plants would come into the market, less and less would be the value probably. So how to handle that in terms of developing the hybrid power plant policies and design methodologies. When we did the large scale analysis in Europe in terms of value of hybrid, so we looked at 2030, and tomorrow Mati will present about the tool which is used for this in terms of modeling the prices and of electricity for 2030. And so we were looking at wind, solar, battery based hybrid for 2030 market in Europe. And this is where we see the value of hybrids. If it is what we see there is the red ones are the dots where probably we will see mainly wind. Yeah, I think this is the better to start with instead of looking at the financial parameters. Yeah, what we see in terms of wind capacity is that this red are the places where we are mainly seeing wind being installed as we have 300 megawatt of contract capacity, like we said in the beginning. So there are only 320, and the best places where you are getting more windy, you are putting more wind, like 360 megawatt here. But in terms of solar, so all these red locations are, there is no solar value, but there are quite a lot of solar value you can find in Poland, mainly because of their vision of they have still quite a lot of coal-based plants there, and if there is high carbon dioxide emission tax, they have to remove those coal-based plants, and then they will need the flexibility in their system, and that would come from the wind and solar because of the increased availability, and then that comes together with the battery. In terms of battery, we did not see any value of the battery anywhere else except for Poland for the said purpose. Again, the questions, this change, how these maps would change when we bring in the other kinds of markets and other kinds of technologies as well, like it could be the hydrogen or power to X. And then how does the large deployment of hybrid power plants impact the market operation? Right now, we assume all these hybrids are market price taker, but if they start becoming price maker, how is that going to play a role? Next, moving on to a very different topic of control architecture of hybrid power plant. How does it look like? This is done with our, I forgot to mention, but all these works are done by an amazing team of people, tens of people in our department. So I should give the whole credit to the team there. So this is this work is done by Chian, our postdoc in the team. And here, if you look into that, so we have the different layers, starting with the hybrid power plant and the grid connection point here. And then we have the hybrid power plant power collection system. Then we have these busbar connection points or the measurement points for individual wind power plant and solar and energy storage system or auxiliary components, and they have their own power collection systems. And finally comes the assets, which are individual wind turbines or individual PV panels or the battery storage and the STATCOMs or the compensating devices. Then how does the signal share happens between them, and what frequency? That's the major challenge. And which kind of services should be put at which controller, who should have what kind of autonomy. EMS is going in the market and designing how they would bid in the service market or the energy market or the balancing market, but how that is being communicated to the hybrid power plant controller is a question. And how do you make it robust against this failure, so that you should also have the autonomy here. We also we accept the fact that it's not that the EMS should be in the master, but because at the end of the day, the hybrid power plant controller need to meet the requirements at the grid connection point in terms of being it provision of the services or meeting some grid code requirements, or at least meeting the expected power output into the to meet the already made bid in the spot market. Yeah, so the the red are the connection measurement points where we get the measurements at individual asset level, and then the references are being communicated to from the higher control levels, and then the measurements are being communicated back to the external control level. In order to validate this control or those energy management system or any of those methodologies, we need some research infrastructure. And we are agreed, we have a mission and vision at DTU to develop, and we are under developing in different phases hybrid wind power plant research facility, where we will have in the lower level the technologies. So we already in the process of having, we have a wind turbine already, V27 Vestas wind turbine, which is being retrofitted. It's a 225 kilowatt wind turbine, which is being retrofitted to make it a fully rated converter-based wind turbine. And then we will put some battery, lithium-ion battery storage, which will be, and supercapacitors, which will be connected to the DC bus of the wind turbine to provide some grid services. Then we have, this is in the next later phase that we, so this is the grid connection point, and the switchboard, which we already have now, which is 400 volt switch board connection. But we have a vision to have a controllable grid interface at a later point, where we can emulate the grid conditions or the frequency or voltage conditions for different kinds of grid operating conditions, be it LVRT or be it frequency or be it weak grid conditions. On this layer, on top layer, we have the research controllers, which will be sitting in our computers and interacting with the asset level controllers there, and interacting with the external layer again, which can be the meteorological measurements or forecast or the electricity market. Then the Denmark government has a vision to have develop a national energy system transition facility, and I think I'm out of time now. So, but where there is a vision, this is in the government roadmap. So we expect this to come in a couple of years from now, where we connect different facility. In DTU, we have DTU Wind Energy and DTU Electrical Engineering, two different facilities called System Engineering Lab or SUS Lab and Hybrid Wind Facility. But then this will be connected to a test center at LORC, and these test centers we have at Ustaril for large scale wind, the Green Lab in Skive for hydrogen and power takes, but also the microgrids in the Aalborg University facility. All of them will be connected through fiber, and we will have common data access, and we can have the capability to co-run or co-simulate different scenarios. I'll skip the open questions, but I have discussed them in general in the previous. And I think energy management system is something which already has been developed by, already been discussed by Ruji before, but I can quickly go through it, maybe 2-3 slides. Is that what we did? Is that we assumed that if we just look at the revenue and we now considering the battery degradation cost and any cost, if we look at the revenue, where is the biggest potential of the revenue? So what we looked at, we have an oracle case, which means it's a perfect forecast in terms of I don't know what. Yeah, we have a perfect forecast in terms of wind as well as market, as well as so that's the oracle. And then the brown one is when we do not have a perfect forecast. So if having the perfect forecast, then even without the battery, we have the possibility to increase the revenue by 3.9% in the market. And if we just go into the in the spot market, if we just go into the balancing market with the perfect forecast, we get 4.4% increase in revenue. I don't know what's happening, but and then if we go do both spot and the balancing market, then we can have huge increase in revenue, and this is highly driven by the size of the storage. If we increase the energy capacity of the storage, this increases exponentially. But then when we started bringing in the battery degradation together with Ruji in WinGrid project, what we see that there is still the battery cost is so high that the battery degradation cost is weighing back all the increase in revenue in terms of energy arbitrage we get with the battery. So still the wind is, but this is only done at the spot market. But maybe when we bring in the balancing market, it would change a little bit the picture. But however, I think it's still the more highly costly affair to use the battery, and this is done in Nordic network, and so this is highly expensive to use battery. I'll skip those things and go to the discussion now. So hybrid power plant is an evolving technology, and there are many open research questions. When we discuss with industry, generally they are having wait and watch policy for fast movers because still it is evolving and we see more and more hybrids coming up, but still there is not a clear goal of what would be the role of hybrid. Value quantification is still an open question, but looks optimistic when we have even further declining cost of solar and storage. And value is defined beyond LCOE. So for example, different kinds of market instrument, grid services or peak power plants, around the clock power plants, and not about minimizing the cost. And hypothesis is, this is what we are also looking into, that with sector coupling, this value will be further pronounced. And this was my last slide. Sorry, Anka.
No problem. No problem. Thank you, Kaushik, for your very detailed presentation. It's a time for 1 or 2 questions. Please raise your hand, if any. Meanwhile, I have a few questions, but I have one fast. Do you know the time frame for NEST facility?
No, it's in the roadmap, but I think it's in the roadmap, so there is no clear timeline. So
Okay.
that is something in the vision of Danish government, but they haven't decided when.
Okay. No questions? Okay, I take one more. I was just thinking that wind started as onshore